Welcome to this explainer. If you've ever felt completely overwhelmed by AI alphabet soup, terms like LLMs, tokens, or fine-tuning, well, you are in exactly the right place. Today, we're going to demystify the so-called black box of artificial intelligence. We're going to systematically unpack its core vocabulary and turn all that complex terminology into a really intuitive, practical blueprint. Here's our mental map for today. We'll start with the core building blocks, then move to how AI actually learns, categorizing machine learning, speaking the AI language, advanced mechanics in memory, and finally, understanding AI limits. Let's jump right in. Section 1. The core building blocks. Honestly, the best way to understand AI is to think of it less like magic and more like a highly sophisticated manufacturing process. And in that factory, data is our fundamental raw ingredient. We're talking about the raw information gathered from the real world. Modern AI systems don't just inherently know things, right? They have to process billions, sometimes trillions of words, images, and audio files. Without this massive influx of diverse, high-quality data, the entire system is just an empty shell. Next stop is the algorithm. If data is our raw ingredient, the algorithm is essentially the cooking method. It's a very specific set of mathematical rules a computer uses to find patterns in that data. Because think about it, it is mathematically impossible for a human programmer to type out fixed rules for every single complex scenario. Instead, an AI algorithm figures out those relationships entirely on its own. And that whole process brings us to the model. The model is the fully trained chef that emerges from the kitchen. When you use a generative AI assistant on your phone or computer, you aren't actually interacting with the raw data or the algorithms anymore. You're interacting with this final trained model, which is now ready to perform complex tasks and generate dynamic responses for you. Section 2, how AI actually learns. So let's put this assembly line in motion. The process starts with our data and algorithms, which feeds straight into a training phase. This is where the model actually learns. From there, the newly trained model moves into what we call the inference stage, which is where it ultimately produces your final output. It's a continuous, incredibly logical workflow from raw input to generated response. The really crucial difference to grasp here is between training and inference. Training is like sending our model to culinary school. It takes massive computing power to process data sets and constantly adjust its internal parameters until the knowledge is locked in. Inference, on the other hand, is the model actually cooking a meal based on a brand new order from a customer. It's taking that hard-earned knowledge and applying it to generate a rapid response. All right, section 3, categorizing machine learning. There are basically 3 distinct ways this machine learning occurs. First, we have supervised learning, which uses labeled data. That's like explicitly showing the AI a picture and saying, hey, this is a cat, so it can predict known outcomes, like filtering your spam emails. Then there's unsupervised learning. This uses unlabeled data, forcing the AI to discover hidden patterns entirely on its own, like grouping similar customers together based on shopping habits. And finally, reinforcement learning. This is driven by trial, error, and rewards, honestly much like training a dog with treats, where it learns by interacting with an environment. Section 4, speaking the AI language. Okay, so a prompt is simply the order you give to our AI chef. It's the specific instruction used to guide its output. You've probably heard people say prompt engineering is the new coding, and it's true. You are translating your human intent into structured instructions. The quality of the prompt you write directly dictates the quality of the AI's final work. But here's where it gets wild. The AI doesn't read entire sentences exactly like you and I do. Instead, it breaks your prompt down into what are called tokens. A token is just a small unit of text. It might be a whole word, a single syllable, or even just a punctuation symbol. To an AI, human language is just a sequence of these tiny mathematical fragments, and its entire job is just predicting which token should logically come next. Now, all of those tokens have to fit within a context window. Think of the context window as the model's active, temporary memory for a single task. It defines the exact volume of tokens the AI can juggle at once. So if you've ever wondered why an AI suddenly completely forgets a detail you mentioned earlier in a long conversation, well, it's because that information literally just fell right out of its context window. Depending on what we're trying to achieve, we process these tokens using different scales of models. Large language models, or LLMs, are absolutely massive. They have hundreds of billions of parameters, incredibly broad knowledge, and deep reasoning capabilities. But on the flip side, we have small language models, or SLMs. These are much lighter, much faster, and run with way fewer resources. You can sometimes even run them directly on your smartphone, which makes them a fantastic, highly private alternative. Section 5. Advanced Mechanics and Memory. This is where the mechanics get incredibly fascinating. First up, we have embeddings. Embeddings literally turn abstract human concepts into numbers. By converting words into numerical coordinates, the AI places them on a giant mathematical map. This is exactly how the system calculates that words like king and queen sit close together in meaning, or how it differentiates between Apple the fruit and Apple the tech company, based entirely on the mathematical context. But what happens if our model needs to learn a highly specialized new skill? That is where fine-tuning comes in. Going back to our analogy, if we want our general chef to become a master pastry chef, we use fine-tuning. We take that already trained foundational model and slightly adjust its internal parameters using specialized data so it becomes an absolute expert at one narrow purpose, like medical diagnostics or analyzing legal contracts. And then there's RAG, which stands for Retrieval Augmented Generation. This is a real game changer. When a model needs up-to-date, accurate facts that simply weren't in its original training data, it uses this process. First, you give it a prompt. Second, the system actually goes out and retrieves relevant data from an external, trusted database. And third, the AI pulls that fresh data right into its context window to generate a highly reliable, fact-checked answer. Finally, Section 6, Understanding AI Limits. Because AI generates language simply by predicting the probabilities of tokens, rather than having true human understanding, it can suffer from what we call hallucinations. A hallucination is when an AI system produces false, invented, or misleading information, but it makes it sound completely plausible. It confidently presents a totally made-up fact just because the math suggested those words looked good together. Which brings us to a really critical final question. How do we actually keep AI reliable and safe when we know it can hallucinate? Well, we rely on strict guardrails to limit harmful outputs, and we use human-in-the-loop workflows where real people actively review the AI's work. Look, AI is an incredibly powerful engine, but it still absolutely needs a human driver. So now that you've got the complete blueprint to see past the magic and understand the math, what are you going to build with it first?